My name's Melissa Brooks from the Met Office. I'm a senior scientist in the Global Atmospheric Model Development team. So I'll be talking about developing global models and myself. So a bit of an outline. First of all, what is a model specifically of the atmosphere? Talk about the model applications and history. Are they any good? And how do we develop them? I'm going to show that through an example of a very simple change rather than just talking very dryly about admin and processes. Then I'm going to talk about my own personal development over the last couple of years, because one of the things that I have done recently was come out at the Met Office as transgender. I did that just over a year ago, and I did that by PowerPoint. And some people seem to find that interesting enough that they wanted me to talk about that, because it is, someone called it a boss move on Twitter, which was quite funny. It worked pretty well. So first of all, what is a model? I'm just going to start off with a quote here. All models are wrong, but some are useful. So whenever you think about a model, you need to think about what is it used for. And for atmospheric models, there are three main uses. Firstly, we have weather. The weather forecast can be as simple as the app on your phone, which I hope is the Met Office one, obviously, because it's best. Or, the data feeds to civil aviation for flight plannings and that sort of thing. We have climate prediction. So models get used by climate scientists, and they write lengthy reports about understanding climate change and warning about future climate change. And that's through the IPCC process. And so that's a very important thing, but also just as research tools. So here's an example of a fairly recent pure research bit of atmospheric modeling where our model was used to understand the atmosphere of a hot Jupiter. So that's an exoplanet, a planet orbiting another star outside our solar system, but it's a gas giant the size of Jupiter, very near the star. So it's really hot. So it's pretty crazy atmosphere, but the model was used to understand it, just because it's a research thing. So I'm going to talk now about the history of atmospheric models. So before digital computers, the atmospheric modeling was quite relatively simple. We had analytical work that was done by Bjerknes and Rosby, people like that, who were writing down the equations and solving them in idealized environments to understand how weather and climate worked. But there wasn't really any predictability there. That really changed with the work of L.F. Richardson in 1922, and he envisaged a giant hall filled with galleries where people, human computers, would write down and calculate the solutions to discretized, so gridded versions of the equations, and he would conduct them essentially and to make a forecast. And scientifically, this was a really valid idea. It's not very different to what we do now. It's just that with a human computers, it's really impractical. It's not going to actually work. That all changed completely with the advent of digital computers. So right from the get-go, once digital computing moved out of the sphere of top secret things, you have the early pioneers like von Neumann or Charney, and they got going that this is the ENIAC computer here, and that's Charney there. And they got going actually predicting, making weather forecasts. Then there was an explosion of activity. It became a solvable problem. People really started developing it. I'm not going to go into all of it there, but really it all kicked off once computing could go digital. And since then, meteorology has been one of the biggest users of high performance computing since. So what are we actually doing? What are those equations? I don't really want to look at those in detail. They're just there to be complicated. We're essentially representing the movement of air, its momentum, its thermodynamics, its movement of heat. The continuity equation just means that when the wind blows, air doesn't disappear and it's not created by the wind blowing. It's very simple, but it means that air gets sucked around and pushed around. Things get transported and then compressed. So there's a lot of complexity there. There's also complexity in how those are converted into a discrete form, what grids they're on, and then how they move forward in time, how things are moved with the air, so advected, and optimized to do it efficiently. Fortunately, that's all within the realm of the dynamics research team because they do the complicated maths. So the dynamical set core, as it's called, is often referred to just the dynamics. And that's job is to resolve the fluid flow on its resolution and grid. For context, the Met Office uses a regular latitude-longitude grid, and they're at sort of 1 to 4 kilometer grid scales in a limited area, so with just a region, and 10 kilometers on a global model. And then in a climate prediction, that's either 60 or 250 kilometers. But lots of things happen at scales much smaller than that. And we generally kind of refer to that as just the physics. That's all of the processes that are smaller than that, and they need to be represented in some way because their effects are vital to the large scale. We do this with the process of parameterization. It's just representing those small scale things on the larger scale. It can be as simple as just setting things to simple values, or really complicated submodels, models within models. I'm going now in order of sort of approximate spatial scale, starting from the subatomic to the chemical to the scale of mountains. So we're representing sunlight and terrestrial radiation, chemistry, the formation of clouds, interaction with pollutants, the formation of rain and interaction with the surface. Convection here means thunderstorms, and then you've got the whole effects of the land surface and the mountains. So all of those processes need to be represented, and that's not an exhaustive list either. I also need to talk about data assimilation. Very briefly though, this is the process of assimilating all of the available observations to make what we call an analysis. We do this by taking the previous forecast, combined with an understanding of its likely errors and how all of its errors are interrelated. And then also the observational errors, and then those are combined in a physically based, iterative system that minimizes the possible errors to produce the new best possible start condition. It's really important because all the big forecasting improvements come through this. There's also other things to check for the soil moisture and the snow and the sea surface temperature and the sea ice. Those are all important things to set in a weather forecast. So those two things, the dynamics and the physics, are kind of our atmospheric model, but we also have, that all takes place in the part of a larger Earth system, whereby we might need to represent land ice or vegetation being dynamic, and because if you're running a climate model that runs for 200 years, you need to know where the forests might have moved to, or where is now a desert. So you need to have all of these complicated other models and components that can all bolt in and be connected together with these kind of produce a global, seamless physical model of the whole thing that can be used on timescales of hours to centuries with a simple weather forecast. Well, it's not simple, but with a weather forecast at the short scales all the way to a full Earth system model used to predict climate in century timescales. Those get built with component models that are put together and bolted together by coupling. So I'm going to show you now some model output. Hopefully this should animate. There we go. So this is operational global model output that was initiated on Saturday just gone until today. The colors are the total 6-hour precipitation. It's slightly lighter where it's snow, but otherwise it's rain. And the contours of the pressure at sea level. And yeah, it looks pretty useful. This is good. This is useful for a forecaster wanting to provide advice. You actually use this to know what the weather was going to be today, 5 days ago. It also looks rather beautiful. It looks nice. It looks kind of right. As a meteorologist, it's working in the right way, and that's important. I'm going to show you two other pretty things. This is a tracer called potential vorticity. Think of it as just the spinniness, but when the air is moved around, it's conserved. Now, this is also at high level, so at about 10 kilometers. And one of the things about this is it just looks really pretty. It just looks like a swirly fluid. If you've ever done an experiment where you've taken a drop of colored dye and dropped it into a moving fluid, you'd get patterns just like that. And on the scale of the atmosphere, upper levels, it is just a swirly fluid. And we live in its kind of little churny bits. On the other hand, over here, this is mineral dust. So this was kicked off from the Sahara last week. And this weather system here is sucking up a plume of mineral dust. And yeah, that was over the UK at the weekend and Saturday. If you were in the southeast, you might have got a dusty car and need to wash your windscreen. And that dust came from the Sahara. It also looks very pretty, and dust is one of my kind of particular specialities. So how did that work? So I'm just going to show now two map plots zoomed in over the UK. This is from the 10-kilometre global model, and this is from a 1.5-kilometre UK model. You can see there's a very significant difference in the amount of detail between the two forecasts. This one here has a lot more detail, but that's not just because of the grid scale. This is particularly because each of these thunderstorm tracks here, that thunderstorm is being represented properly by the solver. It's a fluid system that's properly being resolved. 10 kilometers, that doesn't really happen. So we have a parameterization there that just switches on and represents the average effect of that rainfall. So there's not, the deal of detail is completely different when it comes to thunderstorms between these two systems. Obviously, it's very difficult to get these showers in the right place. So, but they're there. Let's have a look in a bit more detail as well. Let's take a cross section going in height across the south coast. Here is the ice cloud. There's the liquid water cloud, and here's a mixed phase cloud, so the melting layer, and through the front that was there. And this looks exactly like it should, according to theory, or maybe it doesn't go quite high enough. But anyway, enough of that. But it does look really, really good. This, on the other hand, is the mineral dust concentration. This came from the Sahara, and it's over the UK, between sort of 2 and 6 kilometers above our heads, this dust plume. And just in last night, this is very exciting. I've got a plot from the LiDAR, which is a radar, but with a laser. And that was in Kent. And yeah, it's got the dust plume with the right sort of shape, the right timing, the right altitude, and the right amount. So we did a really good job on that. That was absolutely spot on. That's really good. It's also slightly disappointing because whenever the model does a really good job on something, you can't think of anything you have to do to make it better. But this one's particularly good. I'm pleased with that. So how do you make the model better? Well, a lot of it's down to evaluation and diagnosis of the problems. I'm going to show you an example here. This is of some odd eastward propagating weather systems. And there's one there. There it is. The forecasters were reporting these and said they looked odd. And then I started looking for them. Some colleagues started looking. There's another one there. That looks odd. And we started noticing them quite regularly in equatorial Africa and the tropical Pacific. They look odd, but they're underneath clouds. They're always going to be underneath clouds because of how they work. So we can't see see them in detail with satellites. And there's no real ground truth in Central Africa, and certainly not the middle of the Pacific, and certainly no radar. So we kind of just said they look odd, and we'll leave it at that for now because there was nothing more to go on. Fortunately, then we had an event that happened in July 2019 over the UK. This is the operational model forecast, so what was leaving the building as the Met Office forecast. And this is what we call a parallel suite. So this was scheduled to replace the operational forecast in about 2 weeks. We were very close to the go live date. And here it is, just coming. There we go. You see these waves? Bang, 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 bang. There's these funny waves coming in it. Not only is it in the operational model, but the scheduled upgrades got it worse. Oh, that was quite annoying. We were a bit annoyed about that. But unfortunately, we have radar observations here. By measuring the propagation of the weather in the radar observations, we worked out that would be about 19 meters per second, and that was moving pretty much with the flow. The operational model was propagating at 29 and the upgrade at 36. So they're both going about 10 to 15 meters per second faster than they should be. We know from experience this is wrong. It doesn't look right, and it's worse. Well, this kind of feels like it's a solvable problem because we can just look through the differences between this model version and this model version, figure out which ones it can be. So as soon as we do this, we have to do some admin. We have a ticketing system. If you want to change the model configuration, you have to start a ticket, fill in your details with the ticket, with the scientific, what you want to do, given the details. Then have to run some standard tests. And then it goes to some review process, and that requires documentation to pass it. This is all a kind of a quality assurance thing and documentation. Then these tickets get packaged together on a sort of roughly annual release cycle for a new model configuration that we then essentially upgrade everything to. That's the admin. So I'm going to now, looking through the changes, I'm going to talk now about the convection parameterization in brief. So the job of the convection parameterization is to take this little fluffy blob of air that's just found itself somehow more buoyant than its environment, because maybe it's gone over a hill or maybe it's been heated, and that's going to develop into a thunderstorm, maybe. And we do that through some complicated maths that involve the buoyancy of that plume and the mass fluxes in and out of it and things. And what it depends on is something called convectively available potential energy. It's kind of the sum total of the energy of that plume as it rises through its environment. And that CAPE gets used up on a time scale. And that was previously set to 30 minutes. In the new model, it was moved to being a function of the large scale, so the dynamically resolved vertical wind. It defaulted to being a long time scale and was short for active storms. This was very good because we've been told for a long time that one of the reasons why our Indian monsoon wasn't very good is because the CAPE timescale was too short. But when we made this longer, it broke the ability to forecast thunderstorms in kind of Atlantic storms. So we couldn't do both until this came along. It was a really good change, really important. But when there's a thunderstorm, there's an updraft, air going up, and then there's also air coming back down again that's colder. And when that downdraft comes down, it hits the surface and then flows outwards, creating ripples. When the ripple goes up, then a new plume can form, and that can form a new thunderstorm. Now, this is a really important process in the real world for storm evolution and propagation. It's absolutely vital to get this right, but at 10 kilometers, you can't do that properly, but the process is happening. It's kind of like semi-resolved. Also, the CAPE timescale when this air is going up is really fast. And it's also propagating at about the right speed for our wave, which is good too. So what we have here is have an updraft, then a downdraft, a ripple that gives a pushes up, makes a new thunderstorm, an updraft, downdraft, thunderstorm. So basically that process repeats on and on and on, and you get a propagating wave of unrealistic thunderstorms. Two good things have interacted to represent a real phenomena badly. Yeah, it's not good. Fortunately, the solution's really simple. You can take this CAPE timescale and limit it so it doesn't go too fast. Really simple. Not going to do an animation here, but this is just a map from the original forecast. That is the one in the middle is the upgraded forecast where the rain is much worse. Can you see the pink colors are much heavier than the yellow colors in the rain? And here we've got my simple change. And it's not worse anymore. It's in other ones it's better, but yeah, it's not worse, which is great because forecasters will not complain if we've got a fix. They complain all the time. So in order to test this, we're going to rerun a set of past cases. Then we're going to rerun the whole forecast system for 3 months with all of the observation processing and the simulation. And we're going to verify every forecast against every available observation. We're also going to run a 20-year climate model simulation so that this new model produces its own climate. And we're going to compare that climate against everything we can. I'm going to go through that very briefly. So here's one plot. Here is the model bias with height of every 5-day forecast against a radiosonde, so a weather balloon. And there's the change. And it's not very different. It's slightly colder, but not much. This looks okay. And this one here is the average error against all of those observations. And it's no different. This change is neutral. There are a lot of things we can look at, though. We need a way of aggregating that performance into metrics and summarizing them, because otherwise it's just information overload. So here we have lots and lots and lots and lots of different things that we want to check. And the boxes aren't very clear because they're just small and green. Green means good, and it's small means it's not very big. If it was a big change, then there'd be big green boxes or big red boxes. So this is neutral. Yeah, good. In the climate model, we've also got a similar situation where we're going to compare it against lots and lots of things. So this is the climatology of temperature at a particular altitude, at 700, I think. And there's the difference. Yeah. It's basically going between the two colors either side of 0. It's not changed. Here's the climatology of this temperature at 700 from the control and the test. They look identical. It's not changed. And then we'll do this for a lot of things. So there's I counted 294 of these on a single page. So again, we need to aggregate those performance into metrics and summarize them. I don't really want you to look at the details here, just the fact that we can scroll through and scroll through and look for things that are important, things that have changed. And in this case, it hasn't. It's neutral, maybe slightly good, which is good. So here's a timeline for that model change. It all kicked off with a single observed event in July 2019. Then we did a couple of months of initial testing and finalizing the code, getting it to work properly so that the technical people were happy, and it went to a science review to make sure that the scientists in charge of convection were happy, and they were. So it was then lodged in the model code base. Lots of more tests were run, and then by February of the next year, we could propose that to be part of a minor model release. It got reviewed and accepted, and then we had another whole load of tests of that package, and then 3 months of daily forecasts where we run it in near real time just to check. And then within a year, that package of change, GA 7.2.1, as it was called, was handed over to be run by our operational teams in parallel with the main suite. So PS44. That then went live in October. So once it goes live, that's the forecast, the thing that we send out to everyone's app and the Civil Aviation Authority and everything. So this is an unusually quick timescale because it's a really simple change, and also we'd broken something, so we wanted to make it better. So that's talking about the Met now. In summary, atmospheric modeling, global modeling clearly has kicked off in the 20s, but became practical with digital computing in the 50s and 60s. From then, it became a huge area of activity. The atmosphere is a central component of a whole Earth system, and the modeling we do has to reflect that. The application that a model is being used for sets the need for its resolution, what parameterizations are on which components are being used. So whether or not you have convection being modeled directly or parameterized, or whether you have an ocean model or a chemistry model, it's up to it. But weather and climate applications use that same basic model. It's developed for both because we learn a lot from each other's processes, each other's errors. The development cycle evaluates issues, brings in new science, evaluates changes against every observation it can, and then moves on and starts again. That's the normal process. Right. But the past 3 years haven't been normal for me. Along this timescale, I was kind of in the middle of a bit of a dysphoric mental health breakdown at this point, and was having some trouble, and realized that I was needing to transition. And starting hormones, and pretty much around here exactly actually is when I came out as trans to my workplace. So that was good. And then I got COVID and have had long COVID since, which also really sucks. So what I'm going to talk about is actually how I came out at work. So a bit of background, this was GMED, that's our team. And we have a monthly coffee and cake kind of casual meeting where someone gives a brief talk on their work and what they're up to. That happened to be on the day that I was planning on coming out at work because it worked well with the kids' holidays. So I volunteered to do the talk. So this is the talk that I gave. I tried to figure out how best to do this. So what I'm going to do is I'm actually going to switch and give that talk as though it was to a whole other audience. And then I'm going to give a commentary to you. Well, I think that works, but hopefully. So I'm going to switch slides to do the commentary. But basically, imagine you're watching me give a talk to everyone else. Hopefully it works. So here we go. Right. Hello, everyone. It's GMed Coffee. A bit of an unusual one today. In fact, I think this is going to be a first for GMed Coffee, unless I've been really inobservant. I'm actually going to be talking about a personal project. That's something that I've been working on for the last 18 months. It started with a period of introspection, then some reading up, some expert consultation, a bit of social media outreach, and now it's at a stage where I'm going to be bringing what I've learned back into my work at the office, and it's time to let you all know. So what I'm going to say isn't going to make any sense until I've made an announcement. So here it is. I'm transgender. That's something that took me a long time to come to understand and accept. But once I did, I quite quickly realized that I needed to transition if I was going to preserve any semblance of my mental health. So that's what I've been doing. My name is Melissa. Let's change that name. So anyway, there we go. That was the first slide, pretty much done and dusted on the title slide. But my announcement was pretty simple. I just want to say also that about 5 people in the audience already knew, so that allowed me to add a couple of jokes. The reconfiguration and being observant. So reconfiguration's a quite boring technical thing we use to model start files. Now, the jokes worked and they found them funny, but they weren't actually for them. They were for me. They were something that enabled me to start talking, because when you come out, it's a big deal. And you sometimes need to just get talking to the point where you can say the words, I'm transgender, because that's a weird thing to say. Anyway, that worked. And the rest of the thing is all to give them context, prepare and educate my team. So here we go. Anyway, right, let's change the name and put a trans pride flag just for good measure. So what's happening? First of all, I need to say that this is happening. I found that some people find it really difficult to get their head around the fact that it's happening until they see a picture. So this is me. My name is Melissa. My pronouns are she and her. I'm transitioning socially, medically, and legally. Yeah, I really have found that some people need to see a picture to get it. That's something I really found a lot. People just go, what? And then you see a picture and it clicks. And also, hopefully, when I came back to work, it would be less of a surprise because, disappearing as some boringly dressed guy and then just coming back, looking very different, is going to be quite a thing. So anyway, here goes. So my social transition goes public as of now. I just came out. Okay, I came out then. But anyway. I'll be sending an email announcement after the meeting, and as of tomorrow, I will be presenting and living as Melissa all of the time. I'm going to be back at work on Wednesday. Right. That just carried on with an explanation, but also what it was doing was introducing my family. Now, their acceptance has been central to my workings of coming out. They've been wonderful. My ex has also been brilliant at helping them and me to manage all of that. So that's been really important. Someone else also said that it humanizes my transition. It brings me as a complete person to them and shows that I'm accepted by who really matters to me. If I'm accepted by who matters to me, then if they're not accepting, then I don't really care. And also some people, they might be concerned about me, how it's going, and it will allay those concerns. So I think that bit was really helpful. So what's happening? I'm going to talk now about social transitioning. I'm finding a really nice quote from Twitter. I'm not transitioning to become someone else. My transition is letting the world know who I really am. I'm still the same person, the same sense of humor, the same strengths and weaknesses, hopes and fears. But my name's Melissa. I'm a woman even if that seems a bit weird to start with, but that's how I'll be living from now on. Obviously, there's legal transition there of changing that in everything, and that's very long and tedious, and I shan't bore you with it. This will take some getting used to, and I expect you'll make some mistakes. So let me just explain. Naming mistakes we would call dead naming. I am not that name anymore. And pronouns would be, mistakes would be misgenderings. I expect you will make mistakes, but when you do, please just apologize briefly. Let's not make a big deal of it. Just use the correct term and move on. That's fine. If other people make mistakes, I'd like you to gently correct them. I've noticed within my own wider family that when I correct someone, it doesn't really make a change. When someone else corrects that person, then that's when they change. I think that's to do with some sort of like someone's reinforcing that a social norm that this is who I am, and it works much better. So firstly, breaking up transition into a social, medical, and legal thing really helps explain it. They're separate processes, but also I was giving some reassurance here that this wasn't going to be that big a deal. I also wanted to set clear expectations, but not be unreasonable, have a balance with that on dead naming and misgendering. Also just giving people practical advice. I think it's less daunting for them if they know what's expected of them and what to do, just kind of like making it easier for them. Okay, now on medical transition. I'm transitioning because I have gender dysphoria. This was bad enough that I had no choice. So just going to explain gender dysphoria here as a sense of wrongness that comes from the way you live and or from how your body develops, just disagreeing with your gender identity. That kind of sense of self about who you are is like just wrong. It's got lots of different aspects, and some of which are social. Now we live in a gendered society. We live in a society with gendered social norms and expectations. We know that those are arbitrary, but we know what they are and we work within them. Well, we don't have to, but you know, but my dysphoria knows what they are, so that causes problems. Things like how you present yourself, your clothing and your hair, your social interactions and your mannerisms in particular. I mean, I was always, as a kid, my peers always told me I was boying wrong, and it was not okay. Then there's bodily dysphoria, so your body shape in particular, and your size, and where your hair goes, your face, your genitalia sometimes, and particular tells like Adam's apple, and those are just uncomfortable. Vocal dysphoria is a big thing. I used to sing in choirs as a child, and that's given me the ability to modulate my voice to a really large range. And actually, that's really useful, that choral training, because I can now just change the pitch and then sit at a nice level where I'm happy, and it works. Sexual dysphoria is a thing. I'm probably not the forum to discuss, but here we go. By reproductive dysphoria, I mean things like transgender men are often very dysphoric about having a period. It really makes them particularly uncomfortable. And some trans women, very, very uncomfortable about their inability to have kids. Hormonal dysphoria is also difficult to explain. It's kind of like an all-pervasive wrongness in the texture to the experience of existing in your body. Oh, it's a difficult one to describe, but it's just kind of a wrongness. And when you change your hormones, that goes away and it feels good. I also want to talk quickly about gender euphoria. Now, I've put a very bland explanation there, but I want to talk about that a little bit more. So I think gender dysphoria might be an experience that is relatable to everyone, including cisgender people. Sometimes you're just doing something that feels really right for you, makes you really good about who you are. It might be like you're wearing a nice pair of boots and a nice jacket, and it just feels good. Or some men like to wear a suit, and that feels good for them. I don't know. But if you're, as a trans person, if you are not living as who you are, then when you do something that is more who you are, there's a bounce back effect. And that feels really, really good. Like really good. An intense feeling of joy. It's really good description of it. And they're very powerful moments. One thing about them as well is they are pinpoint. This, here, and now feels good and right. That's compared to gender dysphoria, which is miasmic, a toxic fog. You can't figure out where this discomfort comes from. It's really difficult to figure out, and it doesn't make sense. So moments of gender euphoria are like taking a compass bearing. Each time you can gradually move to what feels good and right until you can start figuring out what is right for you, what feels good, what feels normal. And that's really what this is all about. For me, this is what feels normal. And when you feel normal, you can't go back. It just doesn't work anymore. I need to put a disclaimer here. Every trans person's experience of gender dysphoria and euphoria is unique. Some don't get dysphoria. Some don't recognize it until it's gone. So my vocal dysphoria, I didn't recognize that till I figured like, oh, no, I like my voice now. And hormonal dysphoria was just my testosterone went and I felt good. just amazing. So yeah, it's a difficult one, that one. I really wanted this to just say that the main take-home message from this whole thing really is this is my normal, and that realization made my transition essential. There we go. So what are we doing about this? So the most common important thing for trans people's transitions is transitioning socially and hormone replacement therapy. Then for most trans men, breast binding or removal, so top surgery. And for most trans women, things like hair removal. Then there's a bunch of other, hormone replacement therapy does a lot more than most people think. It really is huge. It really changes a lot. Then there's less common things, which are important for some people. I'm not going to go into the list, but I want to say that each of those is specific to one source of dysphoria, and that's all highly personal. So a trans person's priorities will depend on their dysphoria, how it works for them, and their situation. Some are major surgery with risks that are reasonable and, grueling recuperation. They're also expensive. Fewer on the NHS, and that process takes years and years and years. So yeah, all this much more complicated than most people imagine. So to summarize then, I am a transgender woman. My name is Melissa. My pronouns are she and her. I'm still the same person, and my work will hopefully be unaffected. COVID comes along. I've been transitioning now, and I've been on hormones for 7 months. Doing facial hair removal and then hitting cost barriers. So what you need to know, I'll be having a lot of medical appointments. My dysphoria has reduced a lot and things are very much better now. I'm also going through a second puberty with all of the emotional changes that come with that. So hormonally, I'm a 13-year-old girl on a bad day. And the physical changes are just getting going. I'll also be having bad face days where I can't shave or do makeup because of hair removal. So there we go. Please respect my change of name and pronouns, but let's not make a big deal of it. I also want to say the medical side of transition is complicated. I'd like you to treat that with sensitivity and kind of respect appropriate boundaries. So that last bit on respecting boundaries is really important. If you are transgender, so many people will ask you questions they really have no right to be asking you about stuff. It's weird. And obviously, I've now been on HRT for 20 months, and I've moved through that emotional stuff, and it's much more level now.